Welcome to The Explainer. Today, we're diving into a principle that governs pretty much everything that moves from a tiny billiard ball all the way up to massive rocket ships. We are talking about linear momentum. You can think of it as the universe's fundamental accounting system for motion.
So, let's start with a puzzle. It seems simple enough, right? But the physics behind this is actually incredibly powerful. What we're going to do is build up all the concepts you need to solve this, and I promise you, by the end of this explainer, the answer is going to feel totally obvious.
All right, to get started, we first need to get to know the main character of our story today, momentum itself. I mean, what even is this thing that physicists are always talking about?
Well, here it is. Isaac Newton himself called it the quantity of motion. And that is the absolute key. It isn't just about how fast you're going. It's a combination of an object's mass, how much stuff it's made of, and its velocity. So, more mass or more velocity means you've got more momentum. You can kind of think of it as an object's oomph.
And this is where that simple formula, P is equal to mv, becomes really intuitive. It's not just one thing or the other. Of course, a fast car has more momentum than a slow one, but a heavy truck has way more momentum than a light car, even if they're going the exact same speed. This is precisely why a huge football player barreling down the field is so hard to stop. They have an enormous quantity of motion.
Okay, so if an object has all this oomph, how do you change it? Well, you've got to apply a force. In fact, this is how Newton first wrote his second law. He didn't say F equals ma, he said force is the rate of change of momentum. It's a really deep way to think about it, and it leads us right to our next big question. What happens if there's no net force at all?
And that question, well, that brings us to one of the most fundamental, most powerful, and frankly, unbreakable laws in all of science. This is a concept that holds true from the tiniest subatomic particles all the way up to the largest galaxies.
And this is the one big idea you need to take away. In any isolated system, the total amount of momentum is fixed. It's like having $100 in a locked room. People inside can trade it, give it away, maybe even steal it from each other. But the total amount of money in that room is always going to be $100. Momentum can be transferred between objects, but the grand total never, ever changes. It is conserved. So what exactly do we mean by an isolated system? Well, it's basically any group of objects where the forces from the outside don't really matter. So a falling rock, for example, is not an isolated system, because Earth's gravity is a huge external force pulling on it. But, and here's the really clever part, if you define your system as the rock and the Earth together, it suddenly becomes an isolated system. Their gravity is now an internal force between them, and their total combined momentum is conserved.
And this shows the law in action perfectly. So before the collision, you just add up the momentum of each ball to get your total. Then, during the collision, bam, they exert these huge forces on each other. That's Newton's third law right there. And after they bounce off, even though their individual speeds and directions might be totally different, if you add up their momentum again, the total for the system is exactly what it was at the start. Momentum just gets shuffled around, never created or destroyed.
And it all comes down to this one simple, beautiful equation. Total momentum before equals total momentum after. This is the golden rule for figuring out almost any interaction in the universe, from a fender bender to an exploding star. And yeah, it's the exact tool we're going to use to solve our puzzle.
Okay, let's put this law to work. We're about to see how this one simple rule explains a huge range of things we see in the real world, from simple crashes to, rocket science.
Here's a classic example. You've got car A moving along, and it slams into an identical car, car B, that's just sitting there. They lock together. Now, before the crash, all the momentum is in car A. After they couple up, their combined mass is doubled. So to keep the total momentum the same, their speed has to be cut in half. And you can see it right there in the numbers. The math checks out perfectly. Momentum is conserved.
Now, it's worth pointing out that there are two main flavors of collisions. You have elastic ones, like when billiard balls bounce off each other, where kinetic energy is also conserved. And then you have inelastic ones, like our railroad cars, where some of that energy gets lost as heat or sound. But here is the most important part. In both types of collisions, momentum is always conserved.
This brings us to a fantastic question that, really stumps a lot of people. If there's no air in space, what is a rocket pushing on to go forward? The answer is all about the conservation of momentum. Right. The secret is that a rocket doesn't push against the vacuum. It pushes against its own fuel. The system we care about is the rocket plus all the fuel inside it. Before it fires, its total momentum is zero.
It's just sitting there. When it shoots hot gas out the back at incredible speed, that gas has a ton of backward momentum. So to keep the total momentum of the whole system at zero, the rocket has to gain an equal and opposite amount of forward momentum. It's that simple and that beautiful.
All right, we've covered the core concepts, we've got our physics toolkit ready. It is time to go back to that railroad car and finally solve this thing.
So here we are again. Let's look at this one more time, but now we're looking at it through the lens of physics. The car, the worker, the rocks, they're all just coasting along as one happy system. And then the action begins.
Let's just walk through the logic here. Step 1, the system. The car, the worker, and all the rocks are our isolated system. Their total momentum has to stay constant. Step 2, the action. The worker throws a rock backward. That means he gives that single rock a bunch of backward momentum. Step 3, the reaction. To keep the total momentum of the entire system the same, the rest of the system, the car and everything still in it, must gain an equal and opposite amount of forward momentum. Which leads us to the result. The car speeds up. It's the exact same principle as the rocket.
And there we have it. The car speeds up. Every single rock the worker throws off the back acts like a tiny little rocket booster, giving the car another push forward. It's a direct, unavoidable consequence of the conservation of momentum.
Okay, let's really make sure we've got this with one last twist. No throwing this time. What if the worker just lets the rocks drop straight down through a hole in the floor? What happens now?
In that case, the speed stays exactly the same. But why? Because even though the car is getting lighter, no new horizontal momentum is being created. The worker isn't pushing on the rocks. The rocks just fall away with the same forward speed the car already had. And that's the critical difference. Propulsion isn't just about losing mass. It's about forcefully creating momentum in one direction to get that reaction in the other.
So let's just quickly wrap up with the big takeaways. Momentum is mass in motion, P equals mv. In any isolated system, the total momentum you start with is the total momentum you end with. It is always conserved. And this single, elegant idea is the key to understanding everything from car crashes to recoil to how rockets fly. It is truly one of the most fundamental laws in all of physics.
And that leaves us with one final little puzzle for you to chew on. We've just established that only an external force can change a system's momentum. But a car's engine is inside the car. It's an internal force. So how on earth can it make the car accelerate? Think about it. What is the true system here, and what is the crucial external force that's really at play? It's a fantastic little riddle that uses everything we just talked about. Thanks for joining us on The Explainer.